That terrifying tooth on your screen right now. The one that would not even fit inside a human hand. Who do you think it belonged to? That's right, it is a Megalodon tooth. Millions of years have passed, and yet its edge is still as sharp as a knife. The animal that carried this tooth was longer than a city bus, strong enough to tear a whale apart in a single strike. And once, there was no larger predator in the entire ocean. Then, one day, it vanished, or so we think. Because the internet is still full of claims like this. Megalodon never died. It simply went deeper, waiting patiently, in a place where light never reaches. You have probably heard them too. So, is it really down there? In this video, we are going to do two things. First, you will see what this animal actually looked like. And trust me, it is not what the movies showed you. Then we will answer, clearly, the one question everyone asks. Is Megalodon still alive? If you are ready, let's begin. When you hear the word Megalodon, what comes to mind? Probably this: a thick body, a broad head, heavy muscle, basically, a great white shark scaled up several times over. That is more or less how films, games, and documentaries have shown Megalodon for years. The problem is, that image is very likely wrong. Megalodon was not the ancestor of the great white shark. It was not even a close relative. For a long time, we assumed they were related because their teeth looked similar. But that resemblance did not come from kinship. It came from having to solve the same problem. Both animals needed broad, serrated teeth, capable of cutting through large, fatty marine animals. Birds and bats evolved wings independently of each other. And something similar happened here. So, what did the real Megalodon look like? A comprehensive study published in 2025 compared the known vertebrae of Megalodon with those of different shark species. And the result did not point to the thick-bodied monster we are used to seeing. Instead, it suggested a longer, slimmer animal, one that moved through the water far more efficiently. In terms of its general proportions, it may have looked less like a bulky great white shark, and more like an elongated lemon shark. But do not misunderstand. Megalodon was not simply a giant lemon shark. This is only a comparison. It means that its body may have been longer and less bulky than we previously imagined. We still do not know the exact shape of its head. We do not know the exact size or position of its fins. But do you know why a slimmer body makes sense? Because as an animal grows in water, it is not only its weight that increases, so does the drag it faces. A thick body requires enormous amounts of energy to move across long distances. A longer, more hydrodynamic body can cover that same distance, using far less. If Megalodon traveled between continents for millions of years, it owed that success not only to its strength, but to a body built perfectly for the open ocean. So forget the short-range attack machine from the movies. The real Megalodon may have been an open-ocean predator, moving powerfully but steadily, conserving its energy until the exact moment of the strike. But if scientists are still arguing about what this animal looked like, one obvious question comes to mind. Why do we not simply look at its skeleton? You cannot walk into a museum and stand in front of a complete Megalodon skeleton, because no such skeleton exists. Not one has ever been found. The reason is simple. A shark's skeleton is not made from hard bone like that of a dinosaur. It is made largely from cartilage. So when a Megalodon died, its body began to break down quickly. Most of the time, its skeleton did not survive long enough to fossilize. Even though Megalodon was once one of the deadliest predators in the ocean, almost all that remains of it are its teeth. And, far more rarely, its vertebrae, that is all. Scientists are staring at an enormous jigsaw puzzle, with nearly every piece missing. That is why studying Megalodon is less like examining a fossil, and more like solving a crime. You measure the width of a tooth. You estimate where that tooth sat inside the jaw. You examine the diameter of the vertebrae and the growth rings preserved inside them. Then you compare everything with sharks that are still alive today. And here is the strange part. Depending on which modern shark you use as your reference, you end up with a different Megalodon. Use the great white shark, and you get a shorter, bulkier animal. Use a slimmer-bodied species, and you get a much longer one. That is why, for decades, estimates of Megalodon's length have ranged from 15 meters to 16 to 18, and even beyond 20 meters. But eventually, a study involving fossils from Denmark pointed towards something far larger than most of those numbers. Some of the vertebrae found in Denmark measured roughly 23 centimeters across, and those vertebrae changed the discussion completely. Researchers considered the possibility that these fossils truly belonged to Megalodon, and that they represented some of the largest vertebrae in its spinal column. When they ran the calculations, the result was extraordinary. 24.3 meters, roughly 80 feet, an animal as long as 2 city buses, parked end to end, possibly weighing around 94 tons. Its head alone may have been as long as a small car. Its tail, longer than the entire body of many sharks alive today. But we need to pause here, because this number is often badly misunderstood. 24.3 meters is not the average size of Megalodon. It is not the direct measurement of a complete 24-meter animal. No complete individual of that size has ever been found. It is an upper estimate based on several assumptions. The Danish vertebrae must truly belong to Megalodon, and they must come from the correct position within the animal's spine. Most Megalodons were probably considerably smaller, but it is not impossible that a few exceptional giants may have approached that limit. And this is where the real question begins. How does an animal become that large? The answer may surprise you, because Megalodon's journey towards giant size did not begin after birth. It began earlier, inside the womb. How large do you think a newborn Megalodon was? The size of an ordinary shark pup. Not even close. A 2025 study proposed a birth length of between 3.6 and 3.9 meters. That means that on the very day it was born, a Megalodon pup may already have been almost twice the length of an adult human, larger than many shark species alive today. So how could a pup grow that large before it was even born? We may find part of the answer inside the wombs of modern sharks, including species distantly related to Megalodon. In some of these sharks, the eggs hatch while still inside the mother. The developing embryos then feed on unfertilized eggs, which the mother continues to produce. This is called oophagy. In certain species, the process goes even further. The most developed embryo may consume its smaller siblings. This is known as intrauterine cannibalism. But we need to be honest here, because this detail is often exaggerated. No fossilized Megalodon embryo has ever been found. No one has directly observed Megalodon embryos eating one another inside the womb. Our strongest inference is that, like some of their modern relatives, they may have fed on unfertilized eggs. They may also have consumed their siblings, but that has not been proven. It remains an inference. Still, the result would have been the same. Instead of producing hundreds of tiny pups, the mother invested in a small number of enormous ones, and being born at such a size offered immediate advantages. The pup could begin hunting almost as soon as it was born, and the number of predators capable of eating it was dramatically reduced. But did you notice something? This reproductive system contained a dangerous weakness. A species that produces only a few offspring struggles to replace every individual it loses. A small fish may release thousands of eggs in a single season, but the population of a huge, slow-breeding predator like Megalodon could not recover so easily after a major shock. Being born a giant was an advantage for millions of years. But when the world began to change, that same system became a trap that may have accelerated the species' extinction, and simply remaining a giant came with a price of its own, a price that can be measured. Megalodon was not an ordinary cold-blooded fish. Chemical traces preserved inside its teeth suggest that parts of its body could remain warmer than the surrounding water, not fully warm-blooded like a mammal, but its swimming muscles, its brain, and some of its internal organs may have operated at higher temperatures than the ocean around them. This is known as regional endothermy, and we see it today in animals such as great white sharks and mako sharks. The advantage is enormous. Warm muscles can work harder, the animal can enter colder waters, digestion becomes faster, and during an attack, the predator can move with greater speed and power, but every warm engine comes with a fuel bill, and Megalodon's bill was terrifying. A calculation published in 2022 modeled a 16-meter Megalodon weighing roughly 61 tons. According to that model, the animal may have required around 98,000 kilocalories every day. That is not a single exact figure. The estimated range stretches from roughly 78,000 to 123,000 kilocalories. But it is enough to understand the scale. An animal like that could not survive on a few small fish. It needed prey that was large, fatty, and rich in calories. Whales, dolphins, sea cows, seals, large fish, and perhaps any substantial carcass it encountered. Megalodon was not a picky gourmet. It was an opportunistic apex predator, taking whatever could provide enough energy. But consider this. As its body became larger, its options became narrower, because chasing small prey could consume more energy than that prey would ever provide. And here lies Megalodon's true weakness. Its greatest enemy may not have been another monster. It may have been its own metabolism. Its body was an enormous expense that had to be paid again every single day. And to satisfy that appetite, Megalodon relied on one of the most powerful hunting weapons nature has ever produced. To kill prey of this size, a giant body alone is not enough. Megalodon's mouth functioned like a living machine. Its teeth were broad, thick, and lined with edges like saw blades. That structure was not designed only to cut through flesh. It also helped the teeth survive the enormous forces created when the jaw struck the bones of large prey. Computer models published in 2008 estimated that Megalodon could generate between 108,000 and 182,000 newtons at the rear of its jaw. That is roughly 108 to 182 kilonewtons. If the upper estimate is correct, its bite may have been around 10 times more powerful than that of a modeled great white shark. But again, we need to be honest. That force was never measured directly. There is no living Megalodon whose bite can be tested. The estimate comes from scaled-up models of modern sharks, so 182 kilonewtons is not an exact measurement. It is a scientifically reasonable upper estimate. But the most fascinating part is not simply the force. It is how that force may have been used. Fossilized whale ribs, vertebrae, and fin bones have been discovered with deep marks matching large, serrated teeth. This tells us that Megalodon did not restrict itself to soft tissue. It could bite directly through thick bone. According to some reconstructions, an attack on a large whale may have targeted the rib cage. The impact could shatter ribs, damage the lungs, and tear major blood vessels. Within moments, the prey could become helpless. But we cannot say that Megalodon consciously aimed for the heart. A fossil can reveal where a bite landed. It cannot reveal the predator's intention, and Megalodon would not have used the same tactic against every animal. It may have seized smaller whales directly. Against larger prey, it may first have attacked the tail or fins, removing the animal's ability to escape. And sometimes, it may not have hunted at all. It could simply feed from an existing carcass. Megalodon was not dangerous because of brute strength alone. What made it truly terrifying was millions of years of predatory instinct, knowing when to strike, where to bite, and when to conserve energy. In short, it was a nearly perfect predator. The right body, the right weapon, the right appetite, which forces us to ask, if it was so perfectly adapted, why is it not here today? For millions of years, Megalodon thrived. The oceans were warm, small and medium-sized marine mammals were abundant, and shallow coastal waters provided ideal nursery grounds where young megalodons could grow. The world was productive enough to support a predator of this size. Then, during the Pliocene, the system began to break down. The climate cooled, glaciers expanded, sea levels changed, and some of the warm, shallow coastal habitats began to disappear. At the same time, the marine mammals on Megalodon's menu were changing. Some smaller whale lineages vanished. Others began migrating towards colder, but more nutrient-rich waters. Megalodon was partly warm-bodied, but maintaining body heat in colder water required even more energy. So at the exact moment its prey was becoming more difficult to find, the cost of staying alive was increasing. And then new competitors began to spread. Smaller, more economical predators. Early members of the modern great white shark lineage could survive on less food. They could hunt smaller prey, and they may have reproduced more quickly. They may have competed especially strongly with young megalodons, which relied on similar prey in coastal nursery environments. But let us be clear, this was not a war between sea monsters. There is no evidence that groups of great white sharks surrounded and killed adult megalodons. What happened was probably much quieter. A little less prey each year, a little less suitable coastline, slightly colder water, a little more competition. During times of abundance, Megalodon's giant body was an overwhelming advantage. But when scarcity arrived, that body became a debt that could no longer be paid. Megalodon did not disappear because another predator physically defeated it. It disappeared because the economy of abundance that had supported it collapsed. The youngest reliable traces of the species date to around 3.6 million years ago. So, Megalodon died. At least, that is what the scientific evidence tells us. But one corner of the internet refuses to accept that conclusion, and it always points to the same place, the Mariana Trench, the favorite hiding place of everyone who believes Megalodon is still alive. At first, the logic seems reasonable. It is extremely deep, it is completely dark, and humans have explored only a tiny part of it. So, could Megalodon be hiding down there? A habitat cannot be judged only by how hidden it is. The real question is, how much energy does that habitat produce? Sunlight never reaches the deepest parts of the Mariana Trench. There is no photosynthesis. Most of the food chain depends on material drifting down from the surface. Dead plankton, fecal particles, tiny fragments of organic matter, and, very rarely, the carcass of a large animal that sinks all the way to the bottom. This slowly falling material is known as marine snow. Extraordinary creatures do live in the trench, but most of them have extremely slow metabolisms. They conserve energy, they move carefully, and many can survive long periods without food, because regular meals are rare. A predator weighing tens of tons, with a partly warm-bodied metabolism, requires exactly the opposite. It needs frequent, high-calorie food. Online, people sometimes claim that Megalodon could not survive even 3 days in the trench. But 3 days is not an exact scientific figure. No one lowered a Megalodon into the Mariana Trench and started a stopwatch. Still, the reasoning behind the claim remains sound. A predator requiring tens of thousands of kilocalories every day could not permanently survive in an environment where food is so scarce. Let us imagine that one individual somehow survived, feeding on the occasional falling carcass. Even then, one animal is not enough to continue a species. You need males, females, young animals, a complete breeding population, and every one of them must eat regularly. The Mariana Trench simply does not produce enough energy to support a community of gigantic apex predators. And there is another problem. If Megalodon evolved to hunt whales, it would need to rise into the upper layers of the ocean, where whales actually live. And a 20-meter predator approaching the surface is no longer hiding. A predator may disappear into the darkness, but sooner or later, its appetite pulls it back towards the light. Still, let us not rely on ecology alone. Suppose Megalodon really is alive. What evidence should we expect to find? Scientists do not conclude that Megalodon is extinct only because the deep ocean lacks enough food. If Megalodon were alive, it would leave evidence. But no reliable modern evidence exists. Let us examine it, one piece at a time. First, teeth. Sharks continuously replace their teeth throughout their lives. As older teeth fall out, new teeth move forwards from behind. A single shark can lose thousands of teeth during its lifetime. If a living population of megalodons existed today, we should be discovering enormous teeth on the seafloor, teeth that had fallen recently and had not yet fossilized. Instead, every reliable megalodon tooth comes from geological layers, millions of years old. Not one confirmed, fresh example. Second, wounds on prey. Today, scientists can identify killer whale tooth marks on whale bodies. We can recognize the sucker scars left by giant squid. A living megalodon population would leave its own distinctive signature. Enormous, serrated bite marks on modern whales. But no such modern record exists. Third, DNA. Living animals leave traces of themselves in the water. Skin cells, mucus, genetic material. Today, scientists can collect a sample of seawater and detect whether certain species live in that area without ever seeing the animals directly. Of course, not every part of the ocean has been tested, but a global population of megalodons could not remain inside one tiny, isolated corner. These animals would need to travel across enormous territories. Fourth, consider everything humans now place inside the ocean. Commercial fishing equipment, research vessels, sonar, satellite tracking on whales, undersea communication cables, underwater microphones. None of these systems is perfect, but for a breeding population of apex predators, each weighing tens of tons, to survive without leaving one fresh tooth, one clear sonar recording, or one confirmed modern bite mark would be extraordinarily unlikely. We have not explored every part of the ocean, but to detect a giant animal, we do not need to inspect every liter of water, because giant animals do not simply occupy space, they leave an echo throughout the ecosystem, and Megalodon leaves no echo in the modern ocean. But here is the most surprising part. Its disappearance was not only a loss, it may have opened the way for another giant, a giant that is still alive today.